Hey, welcome back to ViViMaT. This is the final talk in the last session, and to introduce our speaker, please welcome my son Toby.
Christian Greiner is...
Hey, wait a minute. Does it really say Greiner there? Oh, okay, really, bummer. I think he prefers Christian Greiner, though.
Okay. Christian Greiner is the leader of the Materials Tribology group at the KIT in Karlsruhe. He studied materials science at the University of Stuttgart, where he got his master's degree.
For his PhD, he worked on bio-inspired fibrillary adhesives at the Max Planck Institute for Materials Research, where he graduated in 2007.
He studied tribological contacts at the nanoscale as a postdoc at Rob Carpick's lab at the University of Pennsylvania.
Ooh, Pennsylvania! Christian joined the KIT in 2010, and his research focuses on the elementary mechanisms acting in metals subjected to tribological load. In 2017, he was awarded an ERC Consolidator grant for a project named tribokey, which is aimed at defining guidelines for the development of materials with tailored friction and wear behavior.
His presentation has the longest title of all ViViMaT talks, and it goes something like this.
Uncovering fundamental subsurface deformation mechanisms in high-purity copper induced by sliding.
Christian, you take it from here.
Thank you very much, Stefan, for this really nice and funny introduction. I appreciate it a lot. I actually really like this kind of Austrian sausage that Stefan and his kids are referring to here. I would also like to thank Stefan for putting this together. I think it's a really great way of, well, meeting, so to speak, having contact to the community and just basically getting through those strange times that we are living in right now. As Stefan also mentioned, I seem to have the longest title of all the talks that are presented here now in this series. And as Stefan already mentioned it, I will not read it again. What I would like to do is I would like to thank the funding agency which is funding the research that I'm presenting to you today, and that's the European Research Council in the form of a consolidator grant. It's also the case, as you might think, that I thank my entire group for their great work and support also now during the Corona shutdowns that we had and that we are having right now. And I would also like to thank, especially thank here, Christian Haug. He is the student who was working on most of the data that I will present to you today. There was actually another student heavily involved, that's Friederike Rübeling. She just defended last week and is now working in industry and is no longer on this picture, which, by the way, as you can see, was taken before social distancing times, right? So looking at a picture like this right now, it looks like, what are those people doing? So with this, we can dive right directly into the talk. And I will not motivate materials tribology because obviously this is a materials tribology session, so I don't really need to do that. What I want to pose and why I'm still showing this is I would like to introduce you to what the key question is that we are following. And the key question for us really is this: where does the energy get dissipated in plastic processes, in metals that are subjected to a tribological load? So that's really what's always in the back of my mind is, what are the deformation mechanisms, what we call the elementary mechanisms to, in this example here, get from a microstructure which is pristine and looks like this, and then over just a couple of sliding cycles, in this case a reciprocating motion, we get to a microstructure that is heavily deformed, where we have here a nanocrystalline layer on top, where we have a finer grained layer underneath, and where very often we have this really sharp boundary between this nanocrystalline layer and the microstructure underneath. Right? And we all know, I mean, that this happens is known for a long time, and by no means we are the first ones to do research on this. And so I want to really emphasize this. I'm well aware that there are not just now currently active groups working on this, but really also in the past, people like David Rigney and many others, Hughes and Hansen, also Doris Kuhlmann-Wilsdorf, and other people have performed research on this, and so we are really standing on the shoulder of giants here. This being said, we actually also think that there is still something we can contribute to this, because we think that the deformation mechanisms are, even though for decades of research, are not yet fully understood. So what is really going on here? And another thing that we're interested in is, well, where does this discontinuity come from? And with this in mind, we, a couple of years ago, set out and thought, well, tribology is so complicated because you always have a body, you have a counterbody, you have to think of the environment. If you have a lubricant, you might have even additives in the lubricant, so you have to take care of chemistry, as we have also seen now in other talks here. So this is just, tribology is just inherently very complex. So what to do with this complexity? So we thought, let's just try to reduce the complexity of our tribological system as far as we can, choose a model material, and then see what we can understand. Let's see if we can really get to the bottom of those elementary mechanisms. Because if you don't do that, in our opinion, you just might get overwhelmed by all the different mechanisms that are going on simultaneously, and so you might not see the tree in front of you because you're just looking at this really big forest of different mechanisms, all acting at the same time. So that is our model system that we have chosen. It's a copper plate, so we use high purity copper, either OFE or OFHC copper, so oxygen-free high conductivity copper, OFE copper, which is even a little bit purer, in contact with a sapphire sphere. Oh, I see the animation is not running so well. KIT just recently, like 2 or 3 weeks ago, changed the template for the PowerPoint slides. And so there are some hiccups I have noticed, but bear with me. So we have a sapphire sphere which is in contact with high purity copper. It's an unlubricated contact. We control the environment it is in. What I will show to you today, it's all in 50% relative humidity air at room temperature, and we do a really mild tribological load. So we have a sphere which has a diameter of 10 millimeters, so 1 centimeter, and a normal force of 2 newtons, which equals a nominal Hertz and pressure of 570 megapascals. And we do this in really slow sliding. And unlike in this animation here, what we do is we just do one trace, right? We just move once from left to right with the sphere and then look at the microstructure that we see. Because if we do this a lot of times, again, there might be many different processes acting at the same time. And so it might get a little bit more difficult to really see what is going on. We actually also follow those processes over the number of sliding cycles, but that would be another story. And as I'm sure a couple of you have now already seen, actually a while back, by performing experiments like this, we stumbled upon the following phenomenon. So what you see here is a cross section. We are now looking from the side into the wear track, basically, right? So here's the surface, and this is where the sliding is happening. And our sample preparation method is such that we electropolish our copper samples after annealing them and grinding and polishing them. There's electropolishing steps, so we have a very, very low defect density structure to begin with. And now if we just slide the sapphire sphere once, in this case now from right to left over the sample, the following is happening, as you can see here. We'll just do this again. So let's slide again. So the sphere is coming in. And this is now the TM foil after the experiment, after just one trace. And you can see this discontinuity here in the microstructure. There's this dark contrast, which is horizontal to the sample surface. And as I'm also sure a lot of you have already seen in the past, so I will not go into too much detail here, we have figured out that what we see here is the self-organization of dislocations. So this line, if you use high-resolution TEM, results I'm not showing today, and if you really zoom in, you see that this is a structure which is made out of dislocations. That's why we call it the dislocation trace line. And it's really the self-organization of dislocations in the stress field of the moving sphere. And so I will actually show you a first idea how this might happen in a second. So when we saw this for the first time, I was really puzzled by this. I could actually not believe it. I thought it's an artifact basically from the preparation, which it is not. It's not an artifact. We have reproduced this time and again. And if it's a mechanism, right? If it's a deformation mechanism, it should actually also be possible to see this in other materials. It should not be something that is copper specific. And that's something that we have quite a bit tested in the recent months and years. And so I want to show you 3 examples for other materials where we have seen this. So we have, for example, looked at copper manganese alloys, something we published in ACTA this year. And there we also see dislocation trace lines, actually several of them, but the trace line phenomenon is also there in copper manganese alloys. The same is true for copper zinc, in this case now copper zinc 5, where we do see the dislocation trace line. If we go to higher zinc contents and thereby lower stacking fault energies, the picture does change slightly. And we have also looked at, for example, a high entropy alloy like the Cantor alloy, cobalt, chromium, iron, manganese, nickel, where we also see, here you can see it, a dislocation trace line, actually a really sharp, nice dislocation trace line. Here it depends on the counterbody, it actually heavily depends on the counterbody, but under certain conditions, and when the plastic deformation is not too high, when we don't get a lot of adhesive wear, we do see a dislocation trace line. We have also looked at BCC materials like iron or tungsten, and also there we do see this dislocation trace line phenomenon. So it seems to be really a mechanism that you can find at least in a certain range of stacking fault energies in other materials, not just in copper. So the question by then might arise, well, why is this happening? And I also would like to give you here what our first idea is into this phenomenon. That's something we developed together with Las Pastevka. And again, because it's something that we published 2 years ago, I don't want to go into too much details. I want to have enough time for our new results, but I need to introduce this phenomenon for those of you who have not seen it yet, because otherwise it might be pretty puzzling. So what's plotted here is the Hamilton, or Hamilton-Goodman as some people call it, stress field under the moving sphere, which is basically a moving Hertzian contact. And what we are looking at now is at edge dislocations which are oriented in 4 different ways, either like this, 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 or this. And the question that we are posing is, well, how are those dislocations reacting to the stress field? And we are looking at this component of the stress tensor, which is the shear stress in the XZ plane, basically, of the sliding sphere. It's really, again, this cross-section. Well, dislocations like this will be pushed in front of the sphere because of the negative shear stress. Basically, the sphere is moving them in front of it like a snowplow, so to speak. Those dislocations here, they are moving to the right and are just following basically the stress field. Dislocations which are oriented like this will be pushed towards the surface and will leave the crystal. And the most interesting ones are these dislocations, edge dislocations oriented like this, because they will be pushed down further into the subsurface material, but as sliding progresses, these dislocations will now cross over, so over basically the zero shear stress line, which is this solid line here, will cross over to the positive shear stresses and will be pulled up towards the surface again. All other dislocations we don't have to really look at. These are the really interesting ones. So what is happening to them? Are they sucked basically completely to the surface? And the answer is no, actually they are not. Because if you now see where, for example, an iso shear stress line for 5 megapascal is, you can see that the dislocations will not move completely to the surface because you need a finite stress to move a dislocation, right? And so if you look in literature, it's actually old literature from the 60s, 70s, you will find that you need in really well-annealed copper a minimum shear stress to move a dislocation of around 5 megapascals. That's why we plot here the 5 and 10 megapascal iso lines. And so basically what we are assuming is the dislocations are sucked up towards the surface or pushed towards the surface, but not completely to the surface. And so they will stop moving here, and then that's where they will self-organize into this dislocation trace line. And if we look at the depth under the surface where this is happening, it's roughly 150 nanometers under the surface, which is also where we experimentally observed the dislocation trace line. And so with this in mind, actually, we now posed hypotheses, if this picture holds true, if we can explain certain experiment, or if this might explain certain experimental results that we had seen. And you can read up on this in our 2018 Scripta paper. Don't want to go into detail now, but this very simple model, which for sure is not completely correct, I'm not claiming that, basically holds true for many of our experimental results. So we like it. quite a lot, even though always knowing that it's for sure not correct, not completely correct, or it's oversimplified. And one of the things that we did study extensively was influence of the sphere diameter and also of the normal load. Results that I will not show today for time's sake, but we have looked into this. And the other thing that we really want to examine and that we are currently working on is, well, what is this 3D structure of this dislocation traceline phenomenon? Because one has to keep in mind that when you cut TM lamella, what is happening is that due to image forces, you might actually lose, so to speak, certain dislocations, because during the thinning process, image forces might basically suck them out of the material. And so that's why we are now also working on the three-dimensional structure of this phenomenon, and it actually might be a little bit more complicated compared to what we see just in those cross-sections along the sliding direction. So keeping this in mind, basically, one could think and one could argue that what I have shown you so far is perhaps not the whole story. And a hint in this direction was actually handed by us in an experimental result. And that's what I'm showing you here. So what you see again is a TEM foil where we are looking in the cross-section and we are looking at the stem contrast when we take the stem to the scanning transmission electron microscopy images inside our scanning electron / focused ion beam microscope. And the sphere here was again just one trace moving from left to right. The normal load here was not 2 newtons, it was a little bit more. Again, experimental details you can read up in our paper that we published on this year in Nature Communications. And what we know here is that we have a grain boundary in here, but it's not just an ordinary grain boundary, it's a specific type of grain boundary, it's a twin boundary. And so this is the first thing we can notice. We have a twin boundary here, and this is an annealing twin, which during the heat treatment of the material basically happened in the material, in the copper. It's high purity copper again here. And so we know that for all intents and purposes, actually, when we cut also beside the wear track, we can prove this, that this twin boundary, when before tribological loading, was going up like this. So, right, so those annealing twins are really sharp, line-like structures. So we know that before the tribological load, really, in this line would just extend here towards the surface. But no more after the tribological load. After the tribological load, this twin boundary is tilted. It's tilted in sliding direction. That's what we can see here, right? To a degree of alpha. So we have tilted the twin boundary in sliding direction. We also see this dislocation trace line phenomenon, actually two, a lower dislocation trace line and an upper dislocation trace line. What else do we see? Well, we see that we don't just tilt the twin boundary, we see that there's a step, right? We also shift the twin boundary. And now what this twin boundary actually allows us to do is, this is something like an indicator or a silent witness to the processes that have happened under this one trace. Processes that if we look at a structure without a grain boundary, as I have shown you before, we might have missed, right? We might not have seen them. So keeping this in mind, now the question is, well, can we make sense of what we see here? Because this to us was really surprising. When we stumbled upon this, we were like, oh, what's going on here? We need to have a closer look at this, because this might really hint towards mechanisms again, where we have so far only seen this mechanism for the dislocation traceline phenomenon, but perhaps there are actually other mechanisms at play. And so what we can infer from this TM foil, when we think about it, in our opinion, are three elementary processes. The first one is this tilt of the twin boundary. So there is a crystal rotation also accommodated in the transverse direction by the dislocation trace line. So after the sliding, that's exactly what we see here, right? We have the dislocation trace line, and the material above the dislocation trace line is rotated around an axis that is going perpendicular to the screen here, so out, in and out of the screen, in sliding direction. That's also something that we had seen previously and which hints towards this character of the dislocation trace line as a small angle tilt boundary. So this is the first process, and that's actually also something that we would see and that we have seen in the past without the witness of the twin boundary. The second one is what we call simple shear. So we do shear the area of the material above the dislocation trace line. In this case, if we go back to the experimental results, above the lower dislocation trace line in sliding direction. So there's a simple shearing of this material, like a deck of cards basically, right? Even though of course this is a dislocation mediated process, it's not a deck of cards, but you can think about it like a deck of cards that you shear in sliding direction. And this is what we see because of the tilt of the twin boundary. And then we have the step, which means that there's a highly localized shear happening at the lower dislocation trace line in sliding direction. So we move this whole material above the trace line in sliding direction. This whole deck of cards as a whole is now moved. Well, what processes in the material, what elementary processes might be behind that? Well, the first one, so this formation of the dislocation trace line and this rotation around an axis perpendicular to the screen is something that might be accommodated by edge dislocations which have a net character like this, or like this, more like this if we have a sliding from left to right. The second one basically are edge dislocations which are either oriented like this or like this, because they just pass through the material parallel to the sliding surface. So if I move the mouse like this, right, it just moves through here and do not leave any trace behind other than moving the twin boundary. So again, without the twin boundary, we would not know of this process because there is no way post-mortem to know about this. And it's the same type of dislocations, but highly confined at where the dislocation trace line is that is responsible for this highly localized shear. So now that we, in kind of like a thought experiment, have identified those processes and dislocations which might be behind this, the question is, does this make sense? And in order to gauge this, we actually asked colleagues of ours at KIT for help. And what we did here is we looked at this TEM foil by a method that's called ACOM. That's automated crystal orientation mapping. So that's basically taking mapping diffraction spots with a very high resolution on the TEM foil, and by doing so, getting information about the crystallographic orientation inside the TEM. And this is what you can see here. So this is the ACOM result, color-coded in transverse direction. And you can see here the inverse pole figure. So a red color corresponds, for example, to a 100 orientation. And what we see above here, so this green color code, that's the platinum that is deposited prior to cutting the temp foil inside the focused ion beam. That's the electron beam deposited platinum in order to protect the surface or the entire material from beam damage while cutting the temp foil. And what we do see is, yes, we do see different colors, right, left and right of the twin boundary, and also here where this lower dislocation trace line is, there's a change in color from below to above. And now let's see if what we basically, if those three processes make sense. So this highly localized shear. So we can ask the question, how many dislocations do we need to get this? Well, it's a shift of 40 nanometers. That's roughly 160 dislocations with a standard Burgers vector for edge dislocation in copper. And that makes sense, right? It's perceivable that there are 160 dislocations highly confined moving at the lower dislocation trace line. So that, right, if it was just one, we would say, that doesn't make sense. If it's a million, it also not make sense. But to move 160 dislocations in this very beginning of sliding, that kind of makes sense. The next one we're looking at is the simple shear. So if we basically again think of this deck of cards idea, I know that's oversimplified by the way, but that's just bear with me. If we think of this deck of cards, we can ask the question, what is the spacing of dislocations? And if we, for example, there find out that you would need 50 dislocations on each slip plane, that would perhaps not make that much sense. So we can see by how much do we actually tilt, and then we can basically just calculate how many of those, on which number of slip planes do we need a dislocation to move through. And if we do this, we actually see it's roughly every other slip plane, so every other lattice plane here above the dislocation trace line, we need to move a dislocation. And that makes sense, right? Every other, kind of, right? So that kind of makes sense, and that's something one can imagine that this is happening. Crystal rotation. That's another question. So let's just see basically by how much do we move the material or rotate the material. And so that also makes sense. We actually see this. The other thing we wanted to see is, well, what about the twin plane? What about the, what about the twin? Do we destroy the twin in this process? Because again, if we stay in this picture of a deck of cards, we would really just shift the twin plane, or the twin itself. We would not destroy the twin, we would just tilt it. And the way to look at this is to look at the twin plane normal vectors. And those we can figure out from the ACOM data, and we can do so below the trace line, and we can do so above the trace line. And let's just look at them and see what that is. And so we see that the twin planes, or these are the vectors of the normal vectors of the twin, and we can do this from the left and we can do this from the right. But basically what the main result is, without going into too much details, because I actually see that I'm going a bit long here for this talk, but I hope you bear with me, is that we have a misorientation between what would be the ideal normal vector for a twin like this in copper and the one we get experimentally is somewhere between 2 and 5 degrees. And there's not a big difference between below the trace line compared to above the trace line. So basically we have a more or less ideal twin experimentally from below the twin, below the dislocation trace line, and after the simple shear above the trace line, we still have a really nice perfect twin. By the way, it changes a bit above the higher dislocation trace line there, the twin character gets a little bit lost. But this would be going into too much details for now. One can do the similar thing. If it's a coherent twin, right, you can also look at the twin as a 60-degree twist around a 1-1-1 or in a 1-1 plane. And so we can also look here, if we look at a twin like this, what is the misorientation between the 1-1-1 vector and the one we get for this twist, the ideal from this experimentally. And here we have a misorientation between 2 degrees and again around 4 degrees. So this again shows you, yes, we really preserve the nature of the twin. So a lot basic experimental results really speak to this fact that we do get this simple shear for the area above the trace line.
And with this, I would like to conclude. And what I wanted to show you is that this dislocation trace line formation that we have reported on more than 2 years ago seems to be really a mechanism, because we find it in a range of different materials, not just copper alloys, but also high entropy alloys, and also in FCC materials like iron or tungsten. And with the help of this twin boundary as a marker, as a silent witness to the processes that are happening while the sphere is sliding and that we cannot look at in situ, we have identified that there is a simple shear happening. So like in this picture, a deck of cards, we are shearing the material in sliding direction. We have a highly localized shear at a location of the lower dislocation trace line that we have identified in this TM lamella that I talked at length now here in this presentation. And we also find this crystal rotation around an axis that is out of plane, and I didn't talk too much about that, but it's also in line with what other researchers in the literature have identified and what they are talking about. The processes that we have identified seem to be physically reasonable. When we look at the ACOM data, they seem to make sense. And the dislocation trace line formation, that's also an interesting result. It's not impeded by the twin boundary, so it really just seems to go through the twin boundary. And that's also something we have seen when we look at specific grain boundaries. This is how this work actually goes on for us, that we are now looking, for example, also in bicrystals, where at different angles we can slide over specific grain boundaries, and we are also looking at twin boundaries in more detail, even as we speak. So with this, again, thank you very much for listening, thank you very much for watching, and thanks again for Stefan and Carlsen for putting this together. I appreciate this opportunity very much. Thank you.
And we did it! 9 top-notch speakers basically sharing their latest results for free. Thank you, Christian, for being our valedictorian. I hope I don't have to cry. As you are by now probably quite tired of hearing, please put your questions in the comments section below. The next time I hope to see you is at the live Q&A event in a week and a half from now, on December 3rd, 1600 Central European Time. That's 3 p.m. Greenwich Meridian Time and 7 a.m. Pacific. I'll probably be bugging you again a day or two before the event. Until then, please everyone stay safe and healthy and ask lots of questions. Bye.